Welcome to the engineering class for September 23rd. Um, okay, so before we jump into the new material, let me tell you what I found about your submissions. So I've looked over everybody's submission for the homework that was due today. Some of you did an excellent job. Some of you did an outstanding job. Most of you seem to understand quite well what a functional specification needs to be and what it needs to not be. But there's still a few of you who apparently don't yet understand what a functional spec needs to contain and what needs to not contain. So some of you who submitted reports, when you look at your score, you're going to find that I gave you a very low score. And so how about let's talk it over right now. How about you guys? I would like one of you to unmute yourself and explain to the rest of the class what are the things that a functional specification should contain and what are the things that it should not contain. Okay, somebody want to unmute yourself and go ahead here?
It should contain the constraints for the project and what what the project is, but it can't contain how you're going to do it at all.
Okay, all right. I think that's pretty good. Anybody want to add to that? I mean, I thought it was pretty complete, but anybody want to add anything to that? Okay, so let me just add a few things. I think Adam did a good job there, but let me just elaborate. Okay, so what is the task that needs to be accomplished? What are the constraints? And you guys know what constraints are, I hope. Those are the limitations. Those are the things that you can do up to here, but then you can't do beyond this, or you're only allowed to use these materials, or the total cost can only be this much. Those are the constraints. Those are the limitations that are placed upon you. So what is the job that needs to be done? What is the task? Okay. What are the constraints that are put on you? And then also, how are you going to measure these, how good of a job you did? How are you going to test the thing? How are you going to measure it? Okay, those are the important concepts that need to be in a functional specification. And most of you included those things. Some of you did not. And then what are the things that a functional specification must not contain? So somebody whose name is not Adam, please unmute yourself and tell us what are some things that must not be included in a functional specification.
How it's made, like the exact kind of blueprints or instructions on how to make the product.
Okay, all right, yeah, so you shouldn't talk in detail about exactly how you plan to make it, because that belongs in the engineering specification, not the functional specification. Okay, good. All right, so the quick summary, functional specification talks about what is the job that you're supposed to do. It's not supposed to contain any hint about how you intend to do that job, because those details go in the engineering specification. All right, so a few of you, what you submitted was not acceptable because either you didn't include enough detail about what is the job that needs to be done and how do you measure it and what your constraints are. You didn't include enough detail, or some of you, you included things about how you intended to do the job, which you should not have done. That should be saved for the engineering specification, which is what we're going to be working on today. Okay, so any questions about that? All right, so if you got a bad score on the test, now I haven't put them in, or it's not a test, on the assignment. I haven't transferred the scores into Aspire yet, but I have put them into Canvas. So if you look on Canvas, you'll see what your score is. And if you got anything less than an 8, I will allow you to redo it, but the most I'm going to give you is an 8. If you want to get a 10, you got to get it right the first time. But if you redo it, I'll let you have a second shot at it. but the best you can hope to get is an 8. And in order to get that 8, you have to turn in something that would have been a 10 had you turned it in the first time that way. All right, so let's talk now about how we plan to do it. Well, actually, how about let's take a minute and just remind everybody what needs to be done, because there is one group of students that I didn't talk about. There are a few of you who did not turn in anything yet. So let's remind ourselves what needs to be done. So how about Callie, would you please unmute yourself and just tell the rest of the team here, what is your understanding of basically the functional specification? Give us a verbal version of this functional specification.
The functional specification is supposed to include what the rocket needs to do.
Well, yeah, but what I mean is I want you now to tell us that. Okay, tell us, what should the rocket do?
The rocket needs to be able to fly farther than any other paper rocket. And I forgot what else I put in mine.
Okay, how are we going to measure how far it flies? From where to where?
After you launch it, I would assume you just measure it in feet or something.
Yeah, but from where to where? Where do you start measuring? Where do you end measuring?
From where you launch the rocket to where it lands.
Okay, so from where you are standing at the time that you launch the rocket until where it lands. Now, when we did this with the paper airplane, I said that if it bounces or slides, then we'll just measure to wherever the paper airplane ends up. This time around, I want to do it differently. This time, I want to measure to the place where the rocket first hits the ground. So if it bounces, we don't count the bounce. Or if it slides, we don't count the slide. We only measure to the place where it first hits. So you're probably going to want, in fact, you're certainly going to want someone to help you. Either your brother or sister, your parents, your friends, whatever. Get somebody to stand reasonably close to where you expect the rocket's going to land, and then have them mark the location where it first hits the ground. Tell them to ignore bounces, tell them to ignore slides. Okay, and so they're going to mark the location where the rocket first hits the ground, and you are then going to measure the distance from where you were standing when you launched the rocket to where the rocket lands. Okay, and whoever's rocket goes the farthest, that they will be the winner. Now, there are some constraints. So how about Anish? Can you tell us what are some of the constraints that we need to live with?
The rocket has to be the width of a penny.
The rocket or the rocket launcher?
It's the launcher, right?
Yeah.
Yeah.
Okay, well, it turns out they're both going to be pretty close to the width of the penny, but the important thing is the launcher. So I made my launcher using colored paper just to help keep things equal. So my rockets are white and my launchers are green. You don't have to do that. You can make them both white if you want. But the important dimension for the launcher is the diameter of the launcher, and the way to measure it is with a penny. If the penny cannot fit in the launcher, then your launcher is too small. So you need to loosen it up a bit. If the penny can fit in the launcher with a lot of room to spare, then your launcher is too big. And this is all stuff that I was hoping that you would have put in the functional specification, and many of you did, but a lot of you did not. Okay, so the penny needs to just barely fit inside of the launcher. Okay, so the diameter there, that is crucial. Now, what about the length of the launcher? Does it have to be 11 inches long, or is it okay if it's longer, or is it okay if it's shorter?
It can be longer.
It can be longer, yes. And it can also be shorter if you want. So I don't care about the length of the launcher, but I care big time about the diameter of the launcher. Okay, now, you're going to use the launcher as your base when you roll the paper for your rocket. So the rocket, the diameter of the rocket is going to be very, very similar to the diameter of your launcher, but maybe not necessarily the same. Okay, might be slightly different. and obviously it have to be slightly larger. There's no way it could be smaller. Okay. All right. So, but do you have to roll the rocket really tight when you're rolling on top of the launcher, or is it okay to be loose if you want?
It
Well, the
can
answer
be.
to that is that's one of the variables that's up to you.
It can-
to decide. Go ahead.
It can be loose.
It can be loose if you want it to. So this is one of the variables that I want you to play with over the weekend here. Maybe it's better to be tight. Maybe it's better to be loose. Maybe it's better to be somewhere in between. That's one of the things I want you to explore. Okay. All right. So for as far as the functional specification goes, I think we've pretty well covered that. Now, some of you talked about fins and weight and things like that. And you said that when you wrote the functional specification, some of you said that it's okay to have fins on the rocket, but it's also okay to not have fins on the rocket. It's okay to have big fins, it's okay to have little fins. So some of you talked about that in your functional specifications, and I thought that was good. And the people who did it right, if they talked about the fins, they didn't say whether to have big fins or small fins or no fins. They just said that fins are one of the variables that you're allowed to play with in your design. Same thing with the weight in the nose of the rocket, okay? Those of you that really did an outstanding job, you mentioned the fact that you could put weight in the rocket, in the nose of the rocket if you wanted to, but that, you know, we're gonna leave it open to you to decide if you want to, and if so, how much, okay? The length of the rocket, okay? That is also a variable that's up to you. My rocket here, I use the entire paper, so my rocket is 11 inches long. Your rocket doesn't have to be 11 inches long. If you want to make one that's only 5 inches or 8 inches, that's okay. If you want to take two pieces of paper and tape them together so you have a rocket that's 20 inches long or more, that's okay. Okay. You are allowed to make the length of the rocket be whatever you want. And wings. Some of you mentioned that you're allowed to add wings if you think that'll help. And the important thing is that you didn't say whether or not you were going to add wings, because that would have been part of the engineering specification. But you did say that it is an option to play with if you so choose. Okay. All right, those are the kinds of things that I wanted to see in the engineering, in the functional specification. Those of you who got an 8 or lower on the score for your functional specification, you can rewrite yours and resubmit yours. And I encourage you to rewrite yours and resubmit yours, but be aware that the best I'm going to give you is an 8. And in order to get that 8, you have to include everything that we just talked about. Any questions before I move on?
Does it matter where we like measure it from? Like if we launch it, does it matter where we like measure it from, like the wings or the nose of the rocket?
Thank you. That's an
Does it
important
matter?
thing. Yeah, that does matter. So thank you for asking. All right. When the rocket hits, I am like 99% sure that what's going to happen is it's going to fly through the air like this, and as it comes down, it's going to come down like this. So if this is the ground, when it comes down, the nose of the rocket is going to hit first. It's possible that it might not. I mean, if it tumbles through the air as it's flying, then, you know, who knows. But if it flies like a normal rocket, it'll fly like this, and then it'll come. And so the nose of the rocket is what's going to hit. So whichever spot of the rocket hits first, you know, presumably the nose, wherever that hits, that's the spot that you measure to. Okay. And so you're going to measure from the place where you're standing. And I would require that don't measure like from your toes to the rocket. Imagine that there's a circle. In fact, you might even want to draw a circle. And so you draw a circle and you stand so that you are inside that circle. And then you're going to measure from the center of that circle to whatever spot on the ground the rocket touched first when it hit? Thank you for asking that, Silas. That's a good, insightful question. All right, so today let's talk about the way that we could design our experiment. And in fact, what we're going to do, the process that we're going to go through is called design of experiment. It's called DOE, which stands for design of experiment. So, right. So I guess I should, okay, that worked. Sorry. Okay, so DOE is a term that engineers use that so much that if you're talking to somebody who's a professional engineer and you talk about DOE, she's going to know what you mean because it's a term that engineers use all the time. So it stands for design of experiment. And it is a process that engineers use whenever they've got some sort of a thing that they need to design that's got lots of different variables. And it's got so many variables that it gets really confusing. How in the world are you going to test all of the different possible combinations of variables? Okay. There is a procedure that engineers are taught in school and use this procedure to help figure out how to design your experiment in order to figure out which way is the best way to do it. Okay, so what we're going to do is we're going to make up something called a test, okay, called a test matrix. All right, so matrix is a word that I know that you guys have heard, probably in association with the movie The Matrix. Okay, hang on a sec, somebody type something in the chat box. Okay. Okay, so you've all heard of the movie The Matrix, and many of you have probably seen it, but you've certainly heard about it. And basically, a matrix is when you take a whole bunch of information and you put it into a special form where you have rows and tables, right? So let's say we have, or rows and columns is what I meant to say. Okay, so let's say that we got a bunch of different variables. And so what we're going to do is we're going to make up a table that looks something like this. And let me get rid of this just because we're going to need a lot of room up here. Okay, so the first column here, the one that I left as being the largest one, okay, this is where we're going to list all of the possible variables. Okay, that R doesn't look like a very good R there. Is that a little bit better? Now my R and my V look pretty similar there. That's too, I'm being a little bit too fussy here, aren't I? Okay, so in the first column, we're going to list all of the different variables that we could play with as we're trying to optimize the design of our rocket. And so we talked about this the other day. Let's start with this one, fin size. So let's list fin size as one of our variables. And by the way, guys, I would recommend that you get out your notebooks and write this down, because in the document that you're going to turn in for the homework assignment that I'm giving you tonight, which will be due next time we meet, which will be on Monday of next week, in your engineering specification, I want you to show me what is your testing matrix. And everything that we're writing on the board right now, or on the screen, I want it to be in there. So fin size is one of the things that is available to us to play with as we try to optimize the design of our rocket. Okay. So there are different ways we could do this. Let's say that we might have no fins at all. That certainly is an option. Okay, we might choose not to cut slits in the paper, and so we are just going to have a tube with no fins. That's an option. Maybe that might fly better. Who knows? okay? And then the other option here is we could have some small fins. And then the other option is we could have some big fins, okay? And we could also have some intermediate size as well. But tell you what, let's limit our variables to 3 levels. Okay, so 3 levels. Okay, and so one variable is going to be where one of these levels is going to be where our variable is the smallest it could possibly be. And then another one where it's the largest it could possibly be, and then one where it's kind of somewhere in between. So for fins, let's say that we can either go with none, large, or small. Okay. What is another variable that we decided we could play with? Somebody unmute yourself and speak up. What's another variable that might help?
Nose weight.
Okay, the weight in the nose. Okay, so let's list that. Weight in the nose. All right. So in other words, the number of pennies. Okay. All right, that word there that doesn't look very much like the word pennies. I want you to pretend that that's what it is. Pretend that's the word pennies. All right, so, well, again, we don't have to use pennies in there. So for our lowest level, let's say that we're not going to put any pennies in there at all. Okay. And then for the biggest level, we could put 100 pennies in there in theory, but I mean, that's getting a little bit ridiculous. So let's pick what is the largest reasonable number of pennies that we think we might put in there. So maybe 4 pennies or 6 pennies. How about let's go with 4?
5.
5, okay. If you want to go with 5, you could do that. Okay, but pick some number. I'm going to go with 4, but that doesn't mean that you have to go with 4. If you want to go with 6 pennies, I'm okay with that. If you went with 100 pennies, I would think that would be a little ridiculous. Okay, and so then my intermediate level is going to be halfway between whatever I said my lowest level is and whatever I said my highest level is. So for me, my highest level is 4, so that means my intermediate is going to be 2. But if you wanted to go with 6 as your highest level, that's okay. In that case, your intermediate level would be 3. All right, what's another variable that we could play with here?
The size of the plane,
The size of the plane?
of the rocket, my bad.
Oh, you mean the length?
Yeah,
Okay, so the length of the rocket, okay? Because the diameter, that's another one is diameter. Let's hold off on that one. But the length of the rocket. Okay, all right, so you don't have to have a rocket that's 11 inches. So let's pick a small number, whatever you think is the smallest reasonable length that a rocket might be. So I'm going to pick 6 inches. But if you actually wanted to go smaller, if you want to go with the 3-inch rocket, hey, that's okay with me. But for me, I think the smallest reasonable rocket that I might want to go in with is 6 inches. Okay, if I were to take 2 pieces of paper and stick them together, each piece of paper is 11 inches long. So 2 pieces of paper together would be 22 inches. That's the most that I would want to go with. So I'm going to put that down as my biggest one. But if you guys wanted to put 3 pieces of paper together and have a 36-inch rocket, I'm okay with that. So, but this is what I picked. Okay, so I need something that's halfway between 6 and 22. So I'm thinking, let's see, that 28, half of 28 would be 14. Okay. But you
think we
don't
should just
have,
put,
go ahead.
sorry, I think we should just put 11 and a half in there because it's
Yeah,
a normal paper size.
I think that's an excellent suggestion because that's what most people are going to go with, I think. So if we just go with 1 piece of paper, a piece of paper is 8.5 by 11. So if we roll it the way that we've got here, 11, that's a good intermediate value. I like that. Okay. Okay, what's another variable? And by the way, I misspelled length terribly. You guys know that
Oh,
when,
I know a variable. Oh, sorry.
okay, what's your variable?
I would say the type of paper used.
Type of paper, okay? So
Yeah.
type of paper. Okay, so the thinnest kind of paper that I can imagine would be like maybe called tissue paper. When I say tissue, I don't mean like Kleenex tissue. That's not stiff enough, but you know, sometimes when you wrap presents, birthday presents or Christmas presents, some people use tissue paper. Okay. Um, and then thick paper would be like cardstock. Hopefully you guys know what cardstock is. In some of your art classes, you've probably used this really thick paper that's called cardstock. And then our middle here would be just, let's just go with normal printer paper. So let's just say normal printer paper. All right. Now you see I'm kind of running out of space on the page here, but let's add at least one more. And in fact, there are a lot more we could add.
The diameter.
Okay, so the diameter of the rocket. All right. So remember the critical diameter is the diameter of the launch tube, which we said has to be 1 penny. So when we use the launch tube to roll the rocket, remember we could roll that rocket really tight, or we could roll it really loose. So how about instead of calling it diameter of the rocket, let's say the tightness. That's supposed to be an S.
Okay.
Tightness of the rocket. Okay, so now this one's gonna be hard to put a number on it, but let's just say that one option is to roll that baby really tight. Another option is to roll it really loose. And then somewhere we'll have medium. Now, I realize that this isn't sounding very scientific. It's better if I can put some sort of a number on what do I mean when I say tight or what do I mean when I say loose, but that's kind of hard to do. So let's just kind of leave it at this.
You could do like twice the diameter or exactly the diameter.
There are ways we could do it, but let's just leave it like this. Let's just say, let's say tight, medium, or loose. And now there are other variables we could play with. Anybody think of some other variables that we could play with?
The shape of the nose?
Ah, that's an important one. I was hoping somebody would say that. Yes, that's a really important one. So the shape of the nose. Okay, so on my rockets, I just have a flat nose. Okay, but some of you might be tempted. Oops, let me do that again. Okay, some of you might want to go with a really sharp nose, a sharp cone. Okay, and then others of you might want to go with a medium cone. Okay, so yes, the shape of the nose, that could be a very important variable to play with. Any others? All right, I'm thinking you guys have probably captured all of them. I mean, if you really want to, you could do things like with your launch tube here. Some of you might be tempted to take some masking tape and coat the entire surface with masking tape. I mean, when we made it the other day, we only put a little bit of tape on this end and a little tape on this end and maybe a little tape in the middle. But some of you might say, well, you know, that paper is kind of rough there. I wonder if it might work better if we coated the whole thing with tape in order to make it more smooth. Might that possibly help my rocket go farther? Okay, so that's a variable you could play with if you want. I'm not saying you have to. All right, so what I want you guys to do, starting tonight, going through the weekend, is I want you to come up with different ways that we could possibly design our rockets. By the way, this is what we're doing right now is you could consider it to be brainstorming. All right, so some people might say, well, I want a big rocket. Actually, let me switch to a different color here. Some of you might want to say, I want a rocket that has, oh, I hate it when I do that. I clicked the wrong thing. Okay. Some of you might say, I want a rocket that has big fins and no weight in the nose. And let's say it's an 11-inch rocket and it's made out of normal paper and it's rolled really tight and it has a flat nose. Okay. So that might be prototype number 1. Okay, where you have all these variables. Now you see, if we were to really make a rocket that had, if we were to test all of the different variables, we would have to make a couple dozen rockets. And this is why DOE, design of experiment, is such an important skill for engineers to do. Because if we wanted to test every possible combination of fin size and weight size and length and paper and everything like that, we would have to make a couple dozen rockets, and that's just not realistic. So we need some way to figure out which are the variables that we think are the most important, and then we work with those variables and we don't work so much with the others. All right, so step number 1 that I want you guys to do is to write up your testing matrix, right? So before you do anything else, come up with the matrix that we just described, the rows and the columns, and I want you to fill in that matrix so that, so you have the matrix that looks like this. That's step number 1, okay? Step number 2 is I want you to decide what you think the 3 most important variables are. Okay? So let me erase these red lines that I did here. Okay. So after you guys have come up with your testing matrix, I want you to pick what you think the 3 most important variables are. So let's see. How about Silas? I'd like you to make a guess at what you think might be a really important variable.
The type of paper.
Okay, so Silas thinks that maybe type of paper is the most important. So that's one that he would put on his list there. Okay, but somebody else might disagree. All right, Elliot, what do you think of the remaining variables? Which one would you guess is probably most important?
Length of rocket.
Length of rocket. Okay. All right. Very good. Okay. And then how about, let's see. Let's go with Keeler. Okay. What do you think might be another really important variable?
Did you say my name? I can't really hear.
Yeah, Keeler.
What, another variable that would
Yeah,
be
I need.
important? Is that what you said?
Yeah, pick a variable.
Fin size.
Fin
Like,
size.
I mean,
Okay.
or a variable.
All right. Okay. So after we make up our testing matrix, we then decide which of the variables we think are the top 3. So just now we've gone with type of paper, length of rocket, fin size. That doesn't mean that you have to pick those three. If you want to pick a different combination of three variables, that's okay. All right, so now for those three variables, what I want you to do is now we're going to decide what our three prototypes are going to look like. Okay, so everybody is required to make 3 prototypes. Now, if you want to make more than 3, you're welcome to do that. In fact, I encourage you to do that, but you have to make at least 3. So you are going to look at this testing matrix and you're going to use it to help you decide what your 3 prototypes are going to look like. And we're going to focus in on the variables that we think are most important. So let's go with fin size first. So one of your prototypes, you would probably want to use small fins, or actually none. One of your prototypes, make it so it has no fins. And then let's say that you go with the smallest rocket possible, and let's say you go with the lightest paper possible. All right. And then you also need to decide what you're going to do with the rest of these variables too. But I want you to focus in on the 3 variables that you think are the most important. So let's say that those are the 3 settings that we're going to use on our first prototype. And so let's say our first prototype is going to be, let's call it the red prototype. Okay. Then let's go with the green prototype. So our green prototype maybe has fins, but they're small. And maybe it's an 11-inch rocket, and maybe it's made out of cardstock. Okay, so that would be prototype number 2. And then prototype number 3, let's call that the brown prototype. Okay, so then brown prototype would have big fins. Now, you might think that the brown prototype, we should make that be a long rocket, but we don't have to follow that pattern if we don't want. Okay, what we could do is we could let our brown prototype have this. Oops, I hate it when I do that. Oh, okay. Okay, we could make it so that the brown prototype has the same length as our green prototype. Okay, and let's go back to our red here. So let's say our brown prototype is going to have big fins, but it's going to be the same length as our green prototype. And let's say that it's made out of the same paper as our green prototype. Okay. So what we're doing here is we've picked the top 3 variables, and we want the 3 prototypes we make to have different combinations of these 3 variables. Now, what about the other variables that we decided were not so important? Okay, well, if we go changing those things too, then it gets really complicated. So here's what I recommend we do. Okay, after we have picked the top 3 variables that we think are the most important, then let's just go with the medium settings for all of the other variables. So if we've decided that our 3 most important variables are fin size, length, and type, then for the variables that we decided were not the most important, let's just standardize on one. So for instance, all 3 of our prototypes are going to have the same number of pennies in the nose. All 3 of our prototypes are going to be wrapped the same tightness. All 3 of our prototypes are going to have the medium level of nose cone. Okay. Now, the red prototype is going to have everything that you see in blue. All of our prototypes are going to have that, but the fins on our red prototype, well, there aren't going to be fins. But for our green prototype, okay, it'll have small fins, but it'll have the same weight. Okay, does that make sense to everybody? Because if we try to test all of the different variables, it just gets too confusing. So what we're going to do is we're going to pick the 3 variables that we think are the most important, And we're going to make sure that the 3 prototypes that we make have different settings for each of those 3 variables. And then the other variables, the ones that we decided were not so important, we're just going to pick one setting for those, and we're going to keep all of our prototypes so they all have the same settings in our supposedly non-critical variables. They all are the same on those. The only things that we vary are the 3 variables that we think are what we call the critical variables. Does that make sense? So type into the text box. I want everybody to either type yes, meaning yes, that makes sense, or if you're still a little iffy on what I'm saying, then type no. Okay, I'm seeing lots of yeses. I'm not seeing any nos. Okay, good. All right. So let me go back to my whiteboard here. Okay, so here's the test matrix. So for your homework tonight, you need to write up an engineering specification, and you need to show me what your test matrix looks like. And then you need to show me which of the variables you have decided are the 3 critical ones. Now, in our example here, we chose fin size, length, and type of paper as being the 3 critical variables in our example, but you do not have to go with those. In fact, I would encourage you not to go with those. You can pick 3 variables that you want to be your 3 critical variables. So after you've created your test matrix, you're going to tell me which of those variables are what are the 3 that you consider to be the critical variables. And then I want you to tell me what you're going to do for prototype number 1, prototype number 2, and prototype number 3. Now, I did it using colored pen, and that made it easier. So for me, red is my prototype number 1. So I can see that prototype number 1 is going to have no fins, 2 pennies in the nose. It's going to be 6 inches long, and it's going to be made on tissue paper, and it's going to be medium tightness, and it's going to be medium nose cone. My prototype number 2 is the green one. So that means that my green prototype is going to have small fins, 2 pennies. It's going to be 11 inches long. It's going to be made out of normal paper. It's going to be medium tightness, and it's going to have a medium sharp nose. And then same thing with prototype number 3, which for me was brown. So brown is prototype number 3. So prototype number 3 for me is going to have big fins, 2 pennies in the nose. It's going to be the same length as my green prototype. That's okay. It's going to be on normal paper. It's going to be normal thickness. Okay, you guys see how that works? So I need you to tell me what are each of your 3 prototypes going to look like. Okay. So Ibrahim is asking, are you allowed to use 3 prototypes in your video and pick the best one? Okay, that's an important question. Thank you for asking that. I definitely want you to shoot 3 prototypes. I don't need to see the videos from all 3 of them. I only want to see the video for the rocket that you have decided is your best rocket. Okay, so you're going to make 3 prototypes at least. You can make more if you want. Okay, but you need to do at least 3 prototypes. So you're going to make 3 prototypes. You're going to test all 3 of the prototypes. You're going to decide which prototype is the best one. And then you're going to get out the video camera. And then you're going to do it again where you're going to video it, but I only need to see your best video. I only need to see video of your best rocket. I don't need to see video of the other rockets. Okay. Any other questions?
When launching the rocket, do you have to be standing on the same level ground as we're like shooting it?
Yes. Yes, you do need to be on level ground, and you need to be now here. Max, he brings up actually a very important point. Some people are taller than others, and so Max is probably suspicious that maybe the taller person has an unfair advantage in this project. And you would be right in suspecting that. It is true that whoever's taller, they have an unfair advantage. Their rocket is going to go a little bit farther. So I don't know what to do about that. Let's just say that if you are short and you want to stand on a stool to give you an extra foot or so, I would go along with that. But I mean, in reality, I think it's negligible. I really don't think that the difference in height between the tallest of you and the shortest of you is really enough to worry about. Okay. Now, another question that you guys might be wondering is, could you do this inside your homes, or are you going to need to go outside? And the answer to that one is definitely you are going to have to go outside. These little paper rockets, I've been doing this for a couple of years, and I've got students that can make these paper rockets go really, really, really far. So far that even if you live in a really big home, even if you got a huge front room, it's not going to be big enough. It'll hit the wall before it hits the floor. So for sure, you're going to have to test these outside. If the wind is blowing, then wait. It won't be a fair test if the wind is blowing. So wait until a day when the wind is not blowing and then go outside. And make sure you're on level ground. If you're on a hill, then that ruins everything. Be on level ground. Let's see how far they go. So KJ got way ahead of me. So KJ asked about the outside. Hopefully I've answered that. Okay, so let's make sure you understand what your assignment is. Okay, so I need a engineering. I need an engineering specification. That is really important. I need you to make and test 3 prototypes. I need you to send me the video. Now, you don't need to send me the final report just yet. All I need right now is the engineering specification and a video showing me what your best rocket looks like.
And the engineering specification is the matrix, right?
Yeah, the matrix is a big part of the engineering specification, but there's more to it than that.
Yeah, that was just, okay.
Right. Okay, good. All right, I think that you guys are well prepared now to do what we need to do. It's 3:15 right now, or 3:13, I guess. So we still have about 25 minutes left. So I'm going to give you that time to work on your engineering specifications. Hold on, I see some questions here. Do we show which prototype you pick in the engineering specification? Yes. In your engineering specification, I want to see a description of all 3 of your prototypes, okay? Prototype number 1, I want you to tell me what fin size did you use, how much weight in the nose, how long, how tight, all that kind of stuff. Prototype number 2, same thing. Prototype number 3, same thing. I want a verbal description, well, I want a written description of telling me what all 3 of your prototypes look like. Okay, that is part of your engineering specification, right? So I want you to write up the engineering specification. I want you to make 3 prototypes. I want you to test the 3 prototypes. And now let's see, do I need the videos by Monday? Tell you what, let's say that I don't need videos by Monday. I'll wait until Wednesday. Wednesday is when we're going to do the final report. But for Monday, we're just going to do an intermediate report. Okay, so engineering specification, make 3 prototypes, test them, and then let's just talk about the testing results, but I don't need the final report. Okay, last chance for questions.
Yeah, so for the engineering specification, do we have to write out how to make the like directions on how to do it, like in the airplane?
Yes, I do want that. Thank you for asking. Anything else? All right, then before you leave, make sure you type bye into the chat box. Otherwise, you won't get credit for being here. I'm going to turn off the recording. So if you wanted to ask a question that you thought was embarrassing, then I'll turn off the recording and you can go ahead and ask your embarrassing question.